Hello everyone, here's an IB past paper talk through. This is the standard level paper 2 from May 2018. So here we go with question 1. We have an elastic climbing rope being tested. We're fixing one end of the rope to the top of a crane and the other end of the rope connected to a block, initially at position A here in the diagram. Block is released from a resting position and we ignore the mass of the rope. So hopefully we can follow this through, and this is going to be a scenario as it unfolds. So to begin with, there's the block. It's going to fall to this position B, and at position B, okay, it tells us down here the unextended length of the rope is 60 meters. So as the block falls, it's essentially free falling to 60 meters, at which point the rope, or the elastic rope, is then under tension. So as the block reaches position B, the rope is now under tension, and so going from position B to position C, now we have tension in the rope, and this is where we have an elastic effect. There's going to be some forces acting on the block that come from the rope. So we're assuming that there is no force from the rope on the block between position A and position B, therefore it is free falling. Okay, so it says here the block falls freely. So question A, which is worth 2 marks, it says at position B, the rope starts to extend. Okay, that's when we start having that force from the rope, but we're asked to calculate the speed of the block as it is at position B. So essentially, we can ignore the rope in all intents and purposes and think about it free falling from here to here. This is our free fall. All right, so let's write in some things that we know. It starts from rest. So the velocity at position A is its initial velocity. So that's our u, our initial velocity, and that's equal to 0 meters per second. Okay. We also know the displacement. The displacement is the distance it's going to free fall. In this case, it's the 60 meters. So our S, our displacement, is 60 meters. What we're trying to find is V. That's what we're missing. And of course, we're assuming we're on the surface of the Earth, so our acceleration due to gravity is 9.81 meters per second. So this block is in free fall. If I was to draw a free body diagram, here it is. It's got the force of gravity acting on it, and that's it. We're ignoring air resistance. We're going to ignore any interaction with the rope from position A to position B. So A to B, it's in free fall. So we're into our kinematics equations, our motion equations. So we would be referencing the data sheet, obviously, at this point, and we might want to take a quick peek at our motion formulas. Here they are, I'll put them in the bottom. And what we're interested in is we're going to try and find the 3 things that we know and the 4th thing that we don't know. So let's make a bit of a list. Okay, well, we've already put it up on our diagram. U, we know. So we've got U. S, we also know. And A, we also know. What we're trying to find is V. Okay, so let's look at our equations and see which equation has everything we need. Okay, well, let's get my pointer here. There's V, U, but this one has T, so that's not going to be any good. There's S, there's U, oh, but there's T again. So T time is the only thing really we are not interested in. So which equation does not have time in it? Well, that's our V squared equation. So final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So the equation that we're going to need here is this one. So let's go ahead now and see if we can solve. So we're solving for v, and that's going to be v squared is equal to u squared plus 2as. Well, u squared is 0, so that becomes irrelevant. And then we're just going to go 2as square rooted is going to give us that velocity at position B. So let's keep going. V, let's put the numbers in. It's going to be 2 times 9.81. Now, let's just pause for a second and think about directions, because that is very important in this. So the direction of the acceleration is down. So this is a downwards direction. So in a sense, we can think about this as a negative. But the displacement is also a negative because it's going from this position to this position. And the velocity final is also going to be a negative. So if they're all going to be negatives, then I can ignore the negatives and just treat them as positives, recognizing, of course, that this final value will essentially be a negative. Okay, so hopefully that sort of makes sense. So I'm just going to put them all in as positive values, but in my mind I know that they're all in the downward direction, which could be considered a negative. So this 9.81, I'm putting it in as a positive, but I know that it's downward pointing. Anyway, 2 times 9.81 times the displacement, which is 60. Again, that would be in a downward direction. And then the whole thing square rooted. So what do I get? Well, let's see the final velocity, put it into your calculator. You end up with 34, and I'm going to go to 3 significant digits because I've got 3 significant digits here, and so that's what I'm going to match it to. So 34.3 meters per second. Okay, so for part B, we're asked to consider the position C. So just to recap on our situation, the block has fallen in free fall from A to B, and we previously calculated the speed at B. It's then moved from position B to C, at which point the elastic has started to apply a force to the block, such that at position C, the velocity equals 0. So just to add in some detail here, I've just moved it over so we can see a bit clearer. We have the speed here, or the velocity at B, was the speed that we previously calculated at 34.3, and then the block is coming to rest at position C with a 0 velocity. We are told the mass of the block here to be 80, and that the time duration with which this deceleration happens, so the time duration here is 0.759 seconds. Okay, so let's use some of our skills here and think about different ways to solve this. The clue here is that we have an average resultant force. So let's just think about the block at position C. It is going to, you can imagine, as this block has reached the very bottom of its stretch on the elastic, it's going to bounce back up, isn't it? But at position C, at this very moment, it's stationary. But there would be quite a large force pulling it up. We're going to call this the force elastic. It's the force coming from the elastic rope. Of course, there's also a smaller force down here, Fg. And so this unbalanced free body diagram is the reason why there's been an acceleration upwards during between position B and C. There's been an acceleration in the up direction. That's what's decelerated it, because the velocities have all been pointing downwards up until this point, which means to decelerate it, the acceleration would have to be upwards. Now that acceleration has come from the resultant of my free body diagram. So if I was to vector addition the forces on my free body diagram, it would look like this. I would put I'll try and do this to scale. So there's the force elastic that I've got on there. Let's put that on here, F elastic. And then my FG, I'm going to draw these vectors now tail to tip. So the FG is going to be here. That's the FG. And so the resultant is going to go from here to here. This is going to be the F net, which is the resultant. There it is. And this is where my MA is going to come from. So we could probably add on to this, again, just looking at our skills. We could do an F net. So the F net is the sum of all the forces. There's going to be 2 here. So the F net is going to be my MA, and that's going to be one of my forces going up. We'll call that the force elastic, minus the force of gravity going down. So I know the mass, so I could work out Fg, but I don't know anything about this elastic force. However, I do know the mass, and it's possible for me to work out this, this acceleration, which means if I can get this acceleration, I can get this resultant force. So the combination of this is the resultant force, the F resultant, and that's what I'm looking for. So really I'm just looking for F equals ma, and since I know that this F equals ma is the resultant force, that satisfies this piece, the average resultant force. I know the mass, so let's go ahead and see if we can plug this in. I know the mass, well the mass is 80 kilograms. All I need now is this acceleration. So how do I get the acceleration? Okay, well, we're going to use kinematics. I currently know U, I know V, I know T, and so with kinematics, if I know 3 things, I can work out a 4th. So I'm going to find my acceleration. Since I know T, I know the final velocity, and I know the initial velocity, we'll use our kinematic equations. So here's our data sheet. We're looking for the equation that does not have S in it. Well, that's our first one here, isn't it? V is equal to U plus AT. So I'm just going to rearrange that and solve for acceleration. So I can get the acceleration here. So acceleration is V minus U divided by T. Keeping track of those positives and negatives, remember that my velocity at position B, so in other words, this guy here, this is going to be a negative direction, whereas my acceleration is a positive direction. That's important. So keeping those in there, I'm going to get and I've got the time, I'm going to get my acceleration to be 45.191. 45.191, of course, meters per second squared. So that can come up into my F equals ma equation, 45.191 meters per second squared. And that's going to give me my resultant force, this F net. Okay, which is, if I plug that in, 3.62 kilonewtons. And I'm just checking I've got my 3 significant digits. I've got 3 sig digs here. I've got 3 sig digs here. I'm pretty happy with that. Okay, another way that you could do this would be to realize, so let's put a line under that, would be to realize that you are given time. Okay, so you've got 0.759 seconds for time. And there's a change in velocity. There's a delta V, and the change in velocity can be worked out by taking the final velocity minusing the initial velocity. And so since we have 34.3 minus 0, sorry, it'd be 0 minus 34.3, the change in velocity is obviously 34.3 meters per second. And when we look at our momentum equations, we should see, there we go, I've got it there, we should see that we have a force that's equal to the change in momentum over the change in time. Well, the time given, this would be the change in time, and since a change in momentum would be equal to the mass multiplied by the change in velocity, we have that change in velocity here. So I can say that the average force, okay, this average force is the change in momentum over the change in time, and the change in momentum is going to be m delta v. So I'm going to put that in. The m is 80 kilograms, and the delta v is 34.3 meters per second, divided by the change in time, which is 0.759 seconds. So, surprise, surprise, my average force is, if you plug that in, you get 3.62 kilonewtons, which, surprise, surprise, is the same as the other method of doing this. So there's two different ways to do it. The key here is to recognize which variables you're given, what you're trying to find out, go through the process of looking at all the skills that you have, which would be free body diagrams, vector additions, F-net expressions, kinematic equations, and then it's just a case of writing down what you know and doing the problem solving. Okay, so this is part B2, and here we actually have to do a free body diagram. Turns out we've already sort of done that when we did our deep analysis of part B1 in the previous question here. But we'll go ahead and add it on here. There's a diagram given to you, and our job is to sketch on the diagram the average resultant force that acts on the block between B and C. So remember that B and C is when the rope starts to act on the block and it decelerates it down to a zero velocity. So to create that deceleration, as we've said this before in the previous question, there must be a force acting on the block that's bigger. So this arrow, this vector arrow, will be bigger than the vector arrow as a result of the weight. So this will be the average force. I'm going to put that as the force average acting on the block. So force average, I'm just going to state this. This is the force applied by the rope. Okay, so just to be really clear, of course, this arrow down here, oops, that's not very straight, but you get the picture. That's my Fg, the force of gravity. And so if we were to do our vector addition, and we've done this once already, but let's go ahead and do it again. If we do our vector addition, I'm going to have this force average here, the average force applied to the block by the rope. I'm going to go tail to tip, so I might as well use green to match the Fg. That's going to be there. That's my Fg. So the resultant force, the F-net, is this part here. Okay, and that's what we had previously calculated. So just looking at part 3 now, the extra little bit of information here. I'm going to bring this up. I've shrunk down my free body diagram. This is part 3. Let's put it here. Now it's our job to calculate the magnitude of this average force. So I'm calculating this F average, this blue arrow. Remember that previously we had calculated the F-net because we'd said that the F-net was equal to the mass times the acceleration, and we used our kinematics to get the acceleration, and we knew the mass of the block. So we already have this F-net. So to work out the average force by the rope, let's just start out with this F-net expression. So F-net, sum of all forces. Here we go, lots of forces. Actually, there's only 2. This becomes ma, that's the actual acceleration of the block. And then we have the force average of the rope plus the force of gravity. Okay, now we've got to really pay attention to the positives and negatives here because we've got them going in different directions. So let's restate this. We're solving for we're going to solve for this average force, but I really need to make sure that I'm taking care of this negative factor here. The green arrow, the FG, is down. All of the other ones are pointing up. So it's really important that I'm going to treat the acceleration to be up. That's okay. We did that in the previous question. I'm going to treat the force applied by the rope to be up, but I'm going to treat this FG to be negative because it's going in the opposite direction. Okay, that's a very important bit not to miss. Okay, so now we're just solving for the force average. Easy. So force average is going to be mass times acceleration, which is what we previously calculated, plus Fg, which is mg, mass times gravity. So the average force applied by the rope in order to create this scenario, the deceleration of the block down to 0. If you plug everything in, ma comes from our previous question. So there we go, just fill the rest of the values in. Obviously that's mass given in the question. This is my previous value that I worked out for the acceleration using the kinematics, and then mass and gravity. So our solution is to 3 significant digits is 4.40, running out of space, kilonewtons, 4.40 kilonewtons. Okay, so for part C, we are now asked to qualitatively talk about different energy changes that are happening within our system. To begin with, we're looking at energy changes between A and B. So it's worth just repeating that we are talking about essentially free fall. So as the object goes from A to B, it's in free fall, and we're ignoring air resistance, we're ignoring any effect of the rope. So it's essentially just an object being held above Earth's surface and then dropped. So just to sketch that out, and then I'm going to use some of these energy system circles and some of my graphs to represent energies before and after. So what does that mean? Well, if we think about really what's happening is this is the surface of the Earth, this is the object, and when you release it, it goes towards the Earth. So the question is, do we think about only the object? Do we put only the object in the system, in the circle, in which case we have an external factor. This is external. In other words, the Earth is external, and effectively the Earth is doing work on the ball, at which point we would have to talk about work coming into the system. Or our other option would be to put a ring around the Earth as well. We could say that the whole thing is in the system. The Earth and the ball are in the system, and they're interacting with each other within the definition of our system. So I can pick whichever one I want to do. I'm going to pick this one. So I'm going to state what is in my circle. So let's go ahead and do that. So inside my circle, I'm going to just talk about the block and Earth. Since it's the interaction of Earth and the block that causes this free fall, I'm not even going to talk about the rope here because it's irrelevant. We're just talking about this free-falling object. So really all I can talk about here is the fact that the ball, the energy of the ball initially is just gravitational. Okay, so at this position here, all we have is gravitational energy. And then as the ball gets to here, it's kinetic energy. So I'm going to talk about the energy at position A. So the gravitational, actually let's annotate that a little bit differently. That's the gravitational energy at A. And then that's going to change to a different type of energy at position B. It's going to be kinetic energy, and that's at location B. So in terms of my system, I'm going to say that it's completely isolated. If I was looking at this as an alien looking at it from outside, and I could see the entire Earth and the ball, and the rock, the block together, I would say that there's no change in energy of that entire system. What's the change of interest is the change in the block. The Earth effectively hasn't been changed by this interaction, so I'm completely ignoring that. But I can say that there's been 0 external work done, so that's going to be a 0 here, no work done. And before, everything here is before, everything here is after this interaction. So before the interaction, all I had was energy in the form of gravity, and I can make up that value. Let's just say it's this much of a bar chart. It's this much here. And then after the interaction, well, let's just go through and think about the other possible energies. So there's gravitational energy, there's kinetic energy, and I suppose we could possibly talk about elastic energy, because eventually we're going to have an elastic component to our system, but neither of these are in play. So in position A, there's no motion, so there's no kinetic energy, and the elastic is not has not been stretched, so there's no elastic energy either. After the event, the gravitational energy has effectively been used. It's gone, it's 0. The kinetic energy is now represented as the same amount as the initial gravitational energy. And once again, at position B here, because that elastic has not been stretched, that's at 0. So this is a nice easy energy flow diagram. Just to recap, we've shown that there's an energy change from gravitational at position A to kinetic at position B, all within a system. So there's no work done externally, in or out, because we've included Earth in our system. And all of that gravitational energy is being converted to kinetic energy. So if I was to make my statement, I'm going to say I would do a sum energy initial and a sum energy final. I would say that there is gravitational potential energy that's being converted into kinetic energy. If I was to make this algebraic, I would say mgh is 1/2 mv squared. I think the answer key would be looking for some specific words. I would have to say something like gravitational energy is completely converted to kinetic energy. Easy. Okay, part 2. So for part 2, we're looking at moving between B and C positions. So just recall that at position B, it has a velocity and effectively a height here, of an unknown height at this point, and it's dropping down in height, which engages the elasticity of the rope, coming to a 0 velocity at the end. So at this point here, at position C, the velocity is 0 meters per second. At this part here, the initial velocity at B, I think it was something like 34 meters per second. Okay, and so we're going to start our energy diagram by saying that at position B, there is some EK. At position B, there is also some gravitational energy. Remember that at position B, there is no elastic energy whatsoever. So before the event, we can talk about gravitational energy. Yeah, we have gravitational energy. And we also have kinetic energy. So inside my system, I'm saying that there's a block. There's also the elastic rope. And I'm also going to include the Earth in this system. Again, I could have had the Earth outside the system, and then it would have been doing work on the block, but I'm going to put it in the system just so that it's all wrapped up in there. And that means we're going to have no external work. Once again, there's no external work coming in and out, because we're just assuming that there's no heat. Realistically, there would be some heat in that elastic rope, but we're going to ignore that. Okay, also at the beginning, because the rope are at position B, there is no elastic energy. That rope has not been stretched at this point. Okay, so there's an interaction now between the two energies. These energies are changing. There's a transfer happening, an energy change. And it means at position C, we're going to have an entirely new concept of energy, new type of energy that we can talk about here, which is the elastic energy. So the gravitational energy has been used up, it's gone. The kinetic energy is used up because it's got a zero velocity, and it's all elastic. So what I should do actually is make this a bit bigger. I'm going to move this up a little bit. Get rid of that. And this is going to be twice as high as these two. So it's these two combined. And that's, of course, my elastic energy. So hopefully we've shown that as a nice representation. In summary, we can now go ahead and say that our sum energy, or energy conservation, initial and final, can be stated as the gravitational initial plus the kinetic initial plus the elastic initial is equal to the gravitational final plus the kinetic final plus the elastic final. And there's zero elastic to begin with, and at the end we have no gravitational or kinetic. So in other words, the gravitational and the kinetic energy at position B are completely converted into the elastic energy at position C. So we summarize with my scrawly writing. We say that both gravitational and kinetic energy at position B are converted by work done on the block by the elastic rope to 100% elastic energy. Actually, I should probably put at position C. Okay, and the last part, this is part D, we're sort of hypothetically now suggesting how could we find out the elastic constant if we're given the total stretch in the rope, 77.4. So just to visualize that, what it's now saying is that because we were given this value initially, so 60 meters to here, we're now told that actually it's 77.4 meters all the way down. So clearly we can see that this bit in here is 17.4 meters, okay? Not that, that really matters because we're only asked to do this hypothetically. So we could do this two ways. We could think about it we could look at it from A to C all the way down. So let's go ahead and think about that as a conservation of energy concept, initial and final. Well, initially, we would say that it's entirely gravitational energy at position A. So just go ahead and state that there, gravitational energy at position A, because there was no kinetic energy and no elastic energy at position A. And then when it's at position C, it is 100% elastic energy, and that's at position C. What we would need to use is our, let's go ahead and put these in. So gravitational energy would be mgh, and the energy from the elastic would be 1/2 kx squared. Question is, what is x and what is h? Well, we've gone from A to C, so this guy would be the height from A to C. Hopefully you can see that. How much does the elastic stretch? Well, it's not 77.4, so the elastic is going to stretch this. So this would be the x. Okay, so that's one way to get k, and then obviously we're just going to go ahead and solve for this elastic constant right here. The other way to think about it would be potentially from B, actually, from B to C. We could go B to C, and once again we would do our energy initial, energy final. This time we're at position B, so at position B there would be kinetic energy at B plus gravitational energy at B, right? Because at position B, it's still not fully dropped the entire length. We still have this amount to go. So there is still some gravitational energy there. And then obviously at position C, we're back to our 100% elastic energy at position C. So once again, we have our 1/2 kx squared. What are we using for x? Same again. This is the stretch that we get. This is the elastic displacement stretch. That's definitely going to be our x. Let's think about this. What do we got? We've got 1/2 mv squared, and that's going to be the velocity at b. Well, we have that. We knew that from a previous calculation, so that's good. Plus the mgh from position b. So this, we have to be a little bit careful because we're completely, in this scenario, we're completely ignoring A to B. So the height change from B to C is going to be this guy here as well. This is going to be the h. So the 17.4 would be the value that we would use in here for the h. And once again, we're solving for the k. So that's how you would hypothetically do it, using this value in our diagram to figure out which bits to use depending on how you state your system, A to C or B to C.